part of the physics involved in Project PHEBE is based on a process called thermally activated delayed fluorescence, or TADF as we keep calling it. And what that really means is we're trying to find molecules which will convert a triplet state into a singlet state. The singlet state is emissive, triplet state is very weakly emissive, and we want to have as much singlet state emitting as possible in our OLED to make it as efficient as possible. And the type of molecules that we're using have a very special property. They contain a donor element which wants to kick electrons into an acceptor part of the molecule which wants to take those electrons. And the molecules that we've started off looking at the moment are molecules where you have a donor connected to an acceptor and another donor. So it's symmetric, and we call them DAD molecules. And then what I've drawn out in sketch form are the important energy levels of that DAD molecule, and these are the key ones which are involved in this TADF process, the way that we're going to convert the triplets back to singlets. So we have the ground state of the molecule, S0, which is a singlet state. We have the first excited state of the donor part of the molecule. We have the triplet states of both the donor part of the molecule and the acceptor part of the molecule, and these are separate, they don't interact with each other, so we can describe a separate triplet on a donor and a triplet on an acceptor. And then the really important energy levels, the ones which are going to give us the TADF process, the triplet harvesting if you like, are these two levels, called a charge transfer singlet and a charge transfer triplet. And the charge transfer state of the molecule is what happens when the electron has been excited from the donor to the acceptor, so that we get a net charge across the molecule, and the molecule then looks like it's effectively charged, has a very strong dipole moment on it, and it creates these new charge transfer bands, and they're the ones that we're going to use in the OLED. Right there.
Perfect, yeah.
Right. Not too bad. Okay. So, this is a bit like giving a lecture now. Look at the board, look at the board, look at the
camera. Looks good, looks good.
Alright.
Okay.
So let's think. So now we're going to talk about the way in which energy goes when we photo excite. Okay.
Yeah.
So let me think. So I'm going to go up here, and I'm going to have an arrow to there and an arrow to there. And then going to have an arrow down to here. Let me try and explain briefly how the TADF process works. And what I'm going to do, I'll use the energy level diagrams to show what happens when we first do an optical experiment, and then what happens inside the OLED, which is a little bit different. So in an optical experiment, what I'm going to do is I'm going to take my molecule, I'm going to put it in front of the laser beam, and I'm going to excite from the ground state up to the locally excited state of the donor. When I'm up here, a few things can happen. I can get intersystem crossing, so that the singlet donor state becomes a triplet donor state. And I can have the charge transfer process, so the electron gets pushed from the donor onto the acceptor to form the CT state. And there's going to be a competition between this process and that process, and depending on which one has the fastest rate dictates which one is the most likely to occur. And in a lot of molecules we find that actually the rate of this reaction and the rate of the charge transfer reaction is fairly similar, and we get something like about 70% forming charge transfer and about 10% forming the triplet state. And also there's a bit of a competition between the locally excited state that we first form when we shine the laser on it, decaying back to the ground state and not giving off any light. First excited state of the donor. Several different processes can occur to this energy within the molecule. The singlet state of the donor can intersystem cross to become a triplet state on the donor. And in competition with that, we can get charge transfer to form the CT state. So that's the process where the electron is driven from the donor onto the acceptor to form this charge separated CT state. And that's the important state of the TADF process. So these two steps are in competition with each other, and we hopefully have a system where the molecule is very beneficial to this process and we form mostly charge transfer states. We want to try and not have too many states forming triplets. There's also a third possibility that that local excited donor can decay without giving off light. And that's a loss mechanism, and that's really bad, and we need to minimize that. And this will be a problem if these two steps are very slow. That's when this one comes into play. So initially we excite the local excited state of the donor, and we can form charge transfer states on the molecule. The next step is the critical step in understanding the TADF process. It was commonly believed that because the CT singlet and the CT triplet state were effectively isoenergetic, and the molecules were designed to hopefully keep these two states at the same energy, it was hoped that we would get some kind of backwards and forwards motion between the singlet and the triplet CT state, such that any state that found itself in the CT triplet state could, by a thermally activated process, come back to the CT singlet state. That would give good emission of light, and that's what would give the light out of the OLED. That would then leave these states perhaps trapped in the locally excited triplet state of the donor, but if this process wasn't very efficient, that wouldn't matter. We'd get most of this energy coming out. But that is actually incorrect, and the process is a little bit different to this. So the first thing to note is that this interconversion between the charge transfer singlet triplet state is actually a forbidden process. It can't happen. You cannot have a spin flip mechanism that takes you from the singlet CT to the triplet CT, or the triplet CT back to the singlet CT. That's fundamentally a forbidden process. But in these particular molecules that we've designed, especially those where the donor is twisted and is perpendicular to the acceptor, then we get strong coupling between the CT singlet state and this local triplet state of the donor. So in fact we get cycling between these two states. And because there's a small energy gap there, we need the thermal energy to activate this back process, but we're harvesting triplet states from the donor triplet state, and the CT singlet state will convert by an electron transfer spin flip to the local donor. And this is now the TADF step. And that's really important, because now we can understand a lot better what happens when we get charge recombination in an OLED. So one of the main new experiments that we will do as part of this project is to look at the states in the TADF molecules which don't emit light. And the idea being that if you look at the states which emit light, then you can learn so much, but you can't tell where all the losses are. And of course the important thing about increasing the efficiency of a material that you're going to put in an OLED is you want to know where the losses are, and then you want to change the chemistry of the material so that you minimize those losses and you get the most efficient emitter. So one of the postdocs on the project, Mark Etherington, is building a system to just measure what we call dark states. So those states which don't emit light but still take some of the energy that you put into the materials when they're being driven in an OLED. And so by producing this new kind of spectroscopy and these new measurements, we'll be able to understand a lot more about the losses in these materials, and then hopefully feed that information back to the chemists so that we can then develop the materials and minimize those losses to make them the most efficient emitters that we possibly can do. Durham's role in Project PHEBE is to do most of the optical and photophysical measurements of all the new materials that are developed through the project. And what that means is that we're trying to understand how those materials actually work and generate light inside the OLED. And from understanding that basic physics, we can then hopefully help the chemists to develop better materials which are more efficient, produce light in a more efficient way, live longer so that the device lives longer. And then once we have those new generations of materials, we can pass them on to the companies who will then put those materials into their test devices, and then we'll see just how good this new TADF type of emission is in an OLED and how it compares to the current state of the art. Hopefully, if we get our job right, then we'll be better than the state of the art, and there'll be a new kind of OLED, more efficient, longer lasting, more efficient for electricity in your phone, so that your phone can be recharged once a week instead of once a night.